Everyone, it's very nice to see you all. Let me start sharing the screen. Uh, right, do you see the screen right now?
Yes, yes.
Yes.
Very nice.
Okay, good. Christina, thank you for having me here. Thank you for this great introduction. Just to repeat a little bit, my name is Damyr Hadiiev. I'm science practice leader at SoftServe R&D. SoftServe is a global IT consulting company, and we are happy that we had our interaction with Franko National University of Lviv 3 years ago on the matter of quantum computing. And this topic actually reflects the way how we interact with university and how it helped us to boost the whole quantum team. And eventually, like, just to be honest, finding my like dream job inside of company to combine two things that I really love, software engineering or computer science in broader way, and quantum computing and physics, of course. So our strict collaboration on quantum computing started almost 3 years ago from a set of webinars jointly with Department of Theoretical Physics, where we started looking into different problems of quantum computing and maybe different applications of that. And this started as something similar to Journal Club, where we try to review initiatives and kick off this activity within SoftServe with help of Ivan Franko National University. After that, we had a fascinating event that was called Quantum Incubator 2021. And during this incubator, we took many of those brilliant people whom you might see here on this picture. And they are now part of SoftServe, and they work in our quantum research team, solving different problems devoted to various different tracks I will share a little bit in a moment. And also, we expanded the framework that was developed for this specific incubator further to the world, to Singapore, to Australia, and now we have this event recurring together with Lviv National University right now every year. And the framework of this collaboration is next. We have some business challenges. We provide some materials on how to write software that eventually, in the end, quantum applications should go to some people, should be used by people. That's why we focus on writing quantum code right now, as it should be scaled in future and it will work seamlessly and we will have everything set up there. Also, something that worth mentioning, we've completed more than 10 different research projects, from the long one that run for many years to small ones that just evaluate different ideas, and they are kind of reactive to what people want to hear from us in the area. And also, as I mentioned, we have 6 brilliant team members who work with quantum computing, but also expand their expertise to some other directions, like machine learning or artificial intelligence so far right now, to even like enrich the strengths of the skills that we have within the team. So what do we do inside of our applied R&D? Right, we have 4 main tracks that one could think of. First one, and one of the important ones, is the fundamental research devoted to investigating of fundamental properties of quantum systems, and of course, development of some new algorithms, as well as assessing of existing state-of-the-art algorithms there to make sure that we are actually able to reproduce them and to leverage them to some new levels. Another activity is consulting and workshops. For consulting and workshops, we talk to actual people. We try to find the problems in their value chain where quantum computing can actually help them. And of course, you know that there is a lot of quantum buzz, like about what is possible with quantum, what might be possible with quantum, but we need to have a very clear vision on that, and we don't have to overpromise anything to people. That's why we want to solve only meaningful problems. It means that if there is something that is related to material science, most likely it will be considered as higher probability to be adopted by quantum computing. But if we will think about something that will rely on some bold claims on the algorithm complexities or anything like for portfolio optimization or for anything else, we will be rather more skeptical on this topic. And we will say that, okay, we need to wait for better devices or for better error correction to see any signs of progress in this area. Then what we do is research and development as a service. For example, some organization doesn't have their own science team, but they want to evaluate what can be done using quantum computing. They have some problems, exact problems that they would like to solve, and they reach to us, and we try to solve those problems in relatively short time. Sometimes those are really long collaborations lasting for a few years for some tracks, and some of them are really short, like 2-3 weeks assessments of how quantum computing can help. And of course, last but not least is hardware evaluation. We would like to get a very clear vision on the broad landscape of devices that is available there, of broad landscape of quantum devices and quantum tools, not necessarily tools for quantum computing, but also for quantum communication, quantum networking, or quantum key distribution, because we want to have the best context that we can provide to customers that we will work with. So what is brilliant about having the R&D in service-oriented company, you can actually do some research. And here is the map of different research directions that we took in past years. And I'm happy to have Christina here, who actually leads the whole scientific direction within our team. And that's about the quantum machine learning, its fundamental properties, because machine learning and transition to quantum machine learning seems pretty straightforward if you will look to technique of how to implement it. However, if we want to think about capacity measures, or if we want to think about entanglement properties, some things that might actually provide some insights on why those systems could be effective, or will they be effective at all, or how we can harness on their effectiveness to solve problems, for example, of physics that definitely should be the most disruptive ones. That is the main reason for which we need to have fundamental research there. And just to give a short summary, right? What are the challenges of working in applied R&D, right? Where alumni of this program could work in future. First of all, business looks sometimes for very short-term wins, and they want to have measurable value in terms of money that will be like saved or brought to them, to their value chain by applications of quantum computing. And we understand that sometimes it's not possible, especially with current state of technology, right? With current state of hardware, of error correction, of devices readiness. And this is more of a strategic decision that we need to push through. And that's why we have to overcome this typical business challenge on how to convince people not to think about quantum computing as a quick win, rather than strategic opportunity to get the real progress in the things that we develop as humanity. Usually, another problem that appears there is the fact that businesses usually don't care whether you're using quantum computing or you use another tool to achieve the same result. That's why that would be the typical question that they will ask: how we can actually understand that quantum computing brings value. And we need to be very serious on having a strong arguments that fundamental research is capable of introducing new possibilities that we might not even know right now. However, they have a very clear outcomes in the end. Also, we know that business heavily depends on public opinions. So, for example, you heard about all those terms like quantum winter or whatsoever, and this is, I would say, pretty normal situation. We went through the very similar roadmap with artificial intelligence, and today I will continue on comparing those two domains while they are not related, of course, and we cannot compare them directly. However, I see the roadmap there as promising for us, for people who work on quantum technology. And we know that sometimes people adopt some technology really fast, then they don't get the outcomes that they wanted, and then they start saying that this tool is not good enough to provide any outcomes. And then there will be this kind of deflation of expectations and different like bold claims in the public domain. However, if you go with a strong scientific position, most likely you will be able to survive this deflation of interest. You will be able to articulate why quantum computing is still important and why it worth to wait for devices to work or start working on quantum computing right now on the devices that we have, because if we don't contribute to the progress that happens right now, we won't be able to find something new in quantum computing. And of course, we have some deflated timelines, right? If you will look seriously in the promises of different quantum companies out there, they all drew some milestones that we will get this algorithm working by 2030, we will get this algorithm working by 2025, or whatsoever. And now we see that most likely we might not get the good level of accuracy by that moment of time. That's why we need to be very cautious on our promises and also like give realistic expectations to people. Another thing that happens there is uncertainty. Uncertainty, not in our like I guess physical sense here. It's rather uncertainty in what are the things to expect from quantum computing, because sometimes we might get a situation where there is a paper published showing that, okay, we can have a quantum advantage on some very specific problem, and immediately in a very short period of time, you will get another paper that will tell you that, okay, this is totally wrong. We can do it classically. We can simulate it on other kind of devices. And then it transforms to duel of publications that actually leads to nothing. And this uncertainty also frightens people who might be end adopters of the quantum technology. However, with all those challenges that we need to work with in this applied R&D, where we need to solve real life problems in a very short timeline with high complexity, we see some good signs. Currently, we see that deflated expectations are reduced in the overall world. With this so-called quantum winter, people understood that, okay, we need to put a strong effort on research. And that's the only thing that we might think about right now. We might focus on it more and deliver more consistent results to make sure that we will get great progress in the end. And of course, the great sign that governments consistently put quantum as a part of different national strategies. We see it in the grants, we see it in different national programs. We saw it today with different programs devoted to military and security domains. And those are pretty good signs that quantum computing is there and is there for many years, and that's long-term strategy for many people. And also there is one example that I really find encouraging, and there are a lot of different talks about it right now, and that's generative AI, right? I know that I'm speaking about two separate domains, right? And when we say, okay, let's make quantum generative algorithms, that would be just following the trends and trying to implement something interesting. Here, I'm going to talk about something that is strongly different. Concepts of machine learning that lie in the background of modern applications, ChatGPT that we heard, or different content creation things that we can find, or for example, tools to generate the molecules using generative AI applications. They all have first principles that were designed in the middle of the past century. Then afterwards, we saw some first progress in having the classification of different objects, or advanced search, or something else. And now we see a very strong conversational AI that is capable of having a very structured conversation with you for a pretty long time, keeping a long context. Or we have a significant progress in mathematical proofs, where you can go to automated proofing algorithms and get much better results than you have before. And we know that maybe potentially, like we hope, I hope, that artificial intelligence will evolve to this level where it will contribute to development of science, to the level that it will find some new brilliant ideas or new connections. And why do I think that it's important right now? Because we can be encouraged by this example, right? We know that quantum computing is just at early stage. Imagine currently we foresee so many beautiful things that can be an outcome of quantum computing, especially for people who are physicists in quantum physics, right? In understanding how our universe works. And only then on all of those applications that might be like pretty handy for finance, for pharma, etc., etc. But quantum computing at some moment of time will experience such explosion, such growth that will be compatible to what we observe with generative AI. And on this note, I'd like to finish my presentation. Thank you so much.
Thank you, Damyr. Thank you so much for this very, very nice talk. Thank you for being with us. Thank you. And are there any comments, questions, suggestions? Yes, Mike. Yeah.
I want to thank you for your presentation. It was free of nonsense. It was enlightening, and I think it shows why you want to work in Lviv, specifically with SoftServe. I did not hear buzzwords. I heard realism. Thank you.
Glad to hear that. Thank you.
Thank you, Mike, for this comment. Thank you, Damyr, once more again. But maybe we have other questions, comments. Yes, Professor Tkachuk.
Damyr, I'm very glad to see you here. So thank you for your talk. Thank you for presentation. We talk about possibility to build a quantum computer in Lviv. Maybe SoftServe can help with building of this device, quantum device.
Well, so to build quantum device, we need to have hardware specialists, and we definitely have some very top-notch hardware specialists inside of company. Also, we have people who work with algorithms and some people with knowledge of compilers, how should be interaction organized between the hardware and the software out there. The only thing that may be missing right now at SoftServe are people who know how to make experimental setup, right? To implement qubit on its own. And that could be a point of collaboration. And like, we always can have this conversation, definitely.
Thank you.
Thank you all.